This video, I'm going to teach you about open chain and cyclic structure of fructose. As we know, fructose and glucose are functional group isomers of each other. They share same molecular formula, but they have different functional group. In glucose, the first carbon is aldehydic carbon, but in fructose, the second carbon is ketonic carbon. So here we have first open chain structure of fructose, which is represented here. So if you look at here carefully, the first carbon is as CH2OH with the 1 degree alcoholic group. Second carbon is ketonic. Third carbon is COHH. It is as like in glucose. Then we have next fourth carbon as HOH, just like glucose. We have fifth carbon as HOH. Here point to be noted. In the fructose also the fifth carbon has the similar configuration as that of glucose. OH is on the right hand side, so fructose also has a D configuration, followed by sixth carbon as CH2OH. Since fructose is levorotatory, so its optical rotation is with a negative sign. So on that basis, the complete name in the open chain structure of fructose is D minus fructose. D stands for its configuration with respect to fifth carbon adjacent to CH2OH group. So D configuration is due to this particular reason. Minus is for optical rotation of fructose. Alright. Now, as per the Fischer projection, the open chain structure of fructose can be written as follows. First carbon we show as it is CH2OH. Second carbon we show as CO, ketonic carbon. Then here it is third carbon. I'll write here, it's third carbon. Then we have fourth carbon. Then we have fifth carbon, then we have sixth carbon. This is carbon 1, this is carbon 2. So third, fourth and fifth carbon are shown in that way. Alright. So it's a replica of this particular structure. So you can correlate it that. So we can represent open chain structure of fructose whether like this or in that way. This is Fischer projection. Now we are moving on to the cyclic structure of fructose. The cyclic structure of fructose is just like in case of glucose. Only the difference is the cyclic structure of glucose is due to hemiacetal formation. Here it is due to hemiketal formation. What is hemiketal formation? We need to understand that. To understand hemiketal formation, look at the reaction which I am going to write here. This is a ketonic group. So when ketonic group comes in contact of an alcoholic group, here O is negative, H will be positive. Here O is negative, C is positive. We know the reasons. O is more electronegative than hydrogen and here O is more electronegative than carbon. So when these two functional groups, they come in contact of each other, then here hemiketal formation takes place, which is somewhat like that. Here C with this OH will be bonded, so we have OH. Now this positive C gets bonded with negative O. So bond is like that. This is hemiketal formation. So based on this particular reaction, we need to understand the cyclic structure of fructose. Here, very important point to be noted. In the cyclic structure of fructose, the hemiketal formation takes place between second carbon and sixth carbon. Second carbon and sixth carbon. Second carbon we understand it is ketonic carbon and sixth carbon has 1 degree alcoholic group as CH2OH. So to understand that, we'll see this reaction, this particular structure first. Here, this is the complete open chain structure of fructose. The second carbon you see here, it's carbonyl carbon. O has negative, C has positive due to difference in the electronegativities. This is sixth carbon which contains alcoholic group. O is negative, H is positive due to difference in their electronegativities. This positive H gets bonded with negative O. This negative O gets bonded with positive carbon. So in doing so, we have two ways of cyclic structure of fructose. First we look at here. In this case, CH2OH I have written on left hand side and which is bonded with C, second carbon. This is the first carbon, second carbon. And this C gets bonded with OH. Which OH? This O bonded with H. So this is OH. So OH comes on right hand side. Followed by third carbon, OHH, fourth carbon, HOH, fifth carbon, HOH. Just like that. And sixth carbon now, since OH has undergone hemiketal formation with the second ketonic group, so here CH2 will be left, where carbon of CH2 gets bonded with O, which is further bonded with this carbon. So in doing so, let us see, we have a ring of how many members? Let's count. 1, 2, 3, 4, 5, 6. So here we get 6-membered ring. Now, we can represent the cyclic structure in this way also. What is the difference in this and this structure? Only one thing. CH2OH here is on left hand side and OH on the right hand side. And in this structure, OH comes on the left hand side and CH2OH comes on right hand side. Rest everything is just like this structure. So if you remember, in glucose we talked about anomeric carbon. Anomeric carbon is the carbon which differs in the configuration. So in fructose, the second carbon is anomeric carbon. To this anomeric carbon, the OH is on the right hand side. So this becomes alpha D minus fructose. In this structure, anomeric carbon has OH on the left hand side. So this becomes beta D minus fructose. So this is about Fischer projection of the cyclic structure of fructose.